And your axis of rotation in this case, you can set it anywhere you want, but remember, how do we choose where our axis of rotation goes? What do we consider when we want to set our axis of rotation? Right, the unknowns, right? You want to set your axis of rotation so it eliminates some unknowns from your equation. And so here we set our axis of rotation here because we neither knew FTL nor did we know theta. Now you could have set it down here, in fact, and then you would have gotten a third equation, but it would have had two unknowns in it. And then you could have solved those system of three equations by substitution, but it's a little bit complicated to solve three equations with multiple unknowns in each equation, but not impossible. You can certainly do that by substitution. So if you chose your axis of rotation down here, that's okay. Not impossible to solve, just a little more difficult. We just want to make it as easy as possible. Well, shoot, you could have put your axis of rotation right here. Right? It's not a real axis of rotation because the thing isn't really rotating. Uh, so we can set our axis of rotation wherever we want. If you put it here, you would have created an equation with three unknowns. Then you would have had a system of three equations, each of them with three unknowns, which again isn't impossible to solve. You can certainly solve it, but it's difficult to solve. Okay? So we got these equations, and we found that one of them, the one that we wrote with the torques, had only one unknown, so we were able to solve for the tension on the right side. And now you can solve these by substitution. I'm not going to work through this one. We'll do another one by substitution. They all require solving them by substitution in this way, and we've done this before. Are we okay with this? You'll follow what I mean when I say solve it by substitution? Yeah, where you solve one equation for one of the unknowns and then plug that into the other equation. If you're not, come see me. I can help you with the algebra of that. Uh, but I'll be looking for these equations to be clearly labeled. Now think about our take home here. You want to think about what are the forces that are acting on this bar. What are the forces that are acting on it? I have the tension in the rope, right? So, and that's one of the things that I'm looking for. What's another force that I have? The weight of the object. This is an 8-meter bar, so it's going to be acting right about here in the midpoint. And then a third force that I have acting, it's asking for it actually, is the what? Right, where the pivot point. That hinge is causing some force to act on the bar. Now you might be inclined to draw this force acting in this direction. Why would that not be correct? Like it seems like maybe that force should be acting only in the vertical direction. Would that seem that way to you, perhaps? Eh? No, which direction would it be? Would it be in the horizontal direction? Okay, maybe so. So we could also say that maybe it's in this direction. But either one of these will give you a net force in either the x or the y direction that's not zero. So you have to be careful. The actual force of the hinge, it's going to have actually a y component and it will have an x component. So when you consider this force due to the hinge, that force is going to be at some angle. And you can read the problem and it sort of alludes to that because it asks both for the magnitude and the direction. Y'all follow what I'm saying? That the force on the hinge in this case is neither in the x nor the y, that it's actually in both directions. So the force on the hinge is here, and then it has an x component and it has a y component. That's a very important part of this question. It also has some angle, we'll just call it theta. And you're looking for the magnitude of that force and the angle of that force. Okay? A similar problem to what we had before. You'll need to think about what are the sum of the forces in the x, what are the sum of the forces in the y, and then also what are the sum of the torques, and where would you set your axis of rotation? Think to yourself, when you write the torques, where would you set the axis of rotation? Where? Did everybody hear that? Where would you set the axis of rotation? Say it louder. Okay, good. So I'm not going to tell you how to do it, but that would be the best place because why? Why would you want to set it at that place? That's where you have the most unknowns. And it just makes it mathematically easier to solve that system of equations. All right, so that's your little Thanksgiving gift. Let's work a previous problem here, and it's similar to one of the problems that you also have on your take home. Your take home is slightly more complicated because in your take home, let me show you on the take home. We'll work through a couple of problems that are similar to this. In your take home, you have where is it? You have a ladder sitting up against a bar or against a wall, but then you also have a rope, and we have friction. I'm not sure. Yeah, we have friction here too. You have friction in this? Oh no, there's no friction. So it's slightly different, slightly easier, slightly more complicated all at the same time because it has this rope right here and it doesn't have friction. But let's work through this one. This one's similar, and you'll work it by a similar procedure. In fact, they all have the same procedure. You label your forces, you label the positions of your forces, the distances, you figure out an axis of rotation, then you do the sum of the forces in the x, the sum of the forces in the y, and then the sum of the torques around some axis of rotation, or maybe around multiple axes of rotation. All right, so let's try this one. What are the forces that are acting on this bar? Go ahead and you can write out some of the forces that are acting on this bar. Also realize that we have friction both on the wall and on the ground. All right, so I have forces, I have a weight that is acting right here. Let's see, do I know the angle theta? I don't know the angle theta, but I do know that this distance is 2 meters and this distance is 5 meters. So I can figure out that angle theta. It's going to be the inverse tan of zero point 0.4 or 2 over 5. And that angle theta works out to be 66 degrees. So this is equal to 66. Likewise, I'm going to go ahead and label this angle up here. This angle is 24 degrees. It'll become important later. And um, there's our force weight. We know the mass, so the force weight is equal to 100 newtons because the mass is 10 kilograms, then the weight of that object is 100 newtons. We have some normal forces. Where are normal forces acting? A normal force occurs anytime you have a surface. Where do I have surfaces here? I have here. And the normal force is normal to the surface. That's why we call it a normal force. So in this case, the normal force will be up, down, to the side. Which will it be? To the side, right, to the left. So my normal force, I'm going to call it FNW, is in this direction. And then FNG, which I'll draw down here, for the ground, is perpendicular to the surface, normal to the surface in that direction. You're going to have these similar forces that are acting in your take-home as well. Then I also have some frictional forces. Remember, the frictional force will oppose the direction of motion. So if this object had no friction acting upon it, which way would it move? Would it move like this, or would it move like this? The first or second one? Right, it'd slide down, right? If there was no friction, it would the bottom would move out, the top would move down. And so our frictional forces are going to oppose those directions of motion. So think about our frictional force. Is our frictional force here up or down? It's going to be up. My frictional force will be up. And here, left or right, it's going to be to the right. So our frictional forces will oppose the direction of motion. It's not actually moving, but it has a tendency to move. I'll call this FSW. And then I'll call this FSG for the ground. I think that's all the forces that I have. That is all the forces. So now I apply my stability criteria. That is that the sum of the forces has to be 0 and the sum of the torques has to be 0. All right, so the sum of the forces in the x direction and the sum of the forces in the y direction, both of these are equal to 0. You can go and sum up those sum of the forces, making sure, up is positive, down is negative, left is negative, right is positive. So in the x direction, so I can only have a couple of forces. I'm going to write out those sum of the forces of FSG minus FNW. We don't usually see the normal force in the x direction, but in this case we do because we have this vertical surface. This is equal to 0. And then in the y direction, I have FSW plus FNG minus FW. And then this is all equal to 0. Let's just sort of remind ourselves of what we know and what we don't know. Um, let's see. Do I know FSG? Well, I have the coefficient of friction between the ladder and the wall. That's equal to 0.5, so I'll write that up here. Mu for the wall is equal to 0.5. Do I know the coefficient? No, I'm looking for mu of the ground. All right. I know FW. I don't know what either normal force is. So in this case, my unknowns are FNW, FNG, and my coefficient. So those are my unknowns. Uh, if I don't know these FNs, then I don't know these coefficients of these frictional forces either. All right, so now we can write our sum of our torques. Where should we choose our axis of rotation? Hey, Hillary. We're actually going to choose two axes of rotations, and then we'll write two separate equations. Where will those two positions be that we would draw our axes of rotation? Top and the bottom, all right? Actually, we could do either, but you'll see, and you might want to do this on your take-home too, that if you write multiple equations, something might pop itself out to you. So if you find it difficult at first, then maybe choose a different axis of rotation. So we'll take an axis of rotation at the top and at the bottom. The first one I'll do is the bottom. Some of the torques with our axis of rotation at the bottom. So we're taking our axis of rotation for this first one to be right here. And then we write our torques. Now we need to know some angles here. This angle is 24 degrees because they're similar triangles. This angle right here is 66 degrees. 66 degrees because I have two parallel lines. And this angle then will equal to this angle. I think those are complementary angles. This angle and this angle are equal. That's the same as saying these two angles are equal. I also need to know this angle right here. And this angle then is 24 degrees. You know that's 24 degrees because if this is 66 and this is 90 degrees, these two are perpendicular to one another because it's a normal force, then this has to be 180 minus 90 minus 66. So it's going to be 24 degrees. You need to know these angles to find your torques. Remember when you're finding your torque, it's FR sine theta, and your theta is always going to be between the force and the moment arm. And the moment arm runs along the object or it extends from it. So we always need to find the angle between the force and the moment arm. You'll need to do that for your take home as well, because on your take home sometimes you have angles for your forces. So the sum of the torques at the bottom, with the axis of rotation at the bottom. Now you want to figure out which of the forces are clockwise and which of them are counterclockwise. Um, Clockwise or counterclockwise? Don't say it out loud just yet, but think about it. Does this force cause a clockwise motion or a counterclockwise motion when I'm rotating about this axis? Now, which is it? It's clockwise, right. Because if this force alone acted, the ladder would move in that direction, which is clockwise. What about this force, clockwise or counterclockwise? Counter, right. It would move in this direction if only this force was acting. This one, counterclockwise or clockwise or counterclockwise? Think about it. What do y'all think? Counter is right. It'd be counterclockwise. This force, a component of it at least, would cause the ladder to move in that direction. So this torque, due to the weight, will be a negative torque, and these two will both be positive torques. All right, so now I'm going to do the FW first. It's going to be negative FW times the distance, which is 2.5 meters, because the ladder is 5 meters long, times sine of 24, plus FNW times 5 meters times sine of 66, plus, now this is where our friction comes in, but I'm going to go ahead and substitute in here that F is equal to mu times the normal force. And then I'll have a better picture of what are my knowns and unknowns. So I'm going to go ahead and substitute that in. And I think in your take-home, let's see, do you have friction in your take-home? Did we already answer that? We don't have friction. Okay, so it makes solving it a little bit simpler. But here, our friction is FSW, so it's going to be mu W times FNW times 5 meters times the sine of 24. And that's all equal to 0. Let's see what our unknowns are here. I know the weight. I don't know FNW. Do I know mu of the wall? I do. It's 0.5. Oh, but I don't know FNW here. Well, shoot. How many unknowns do I have in this equation? I just have one. Right, so I can solve this equation and figure out what FNW is. And if I do that, I find that FNW is equal to 18. Right? So if I know that FNW is equal to 18, well then the answers just sort of start falling into place, because I also know that FSG is equal to FNW, or because of this equation that I solved up here. So that also means that the magnitude of FSG is equal to 18 newtons. That's required because it's not moving in the x direction, so the x forces all have to add up to equal to 0. All right? So that answers this question, and then it also answers this question. And now I'm left with what is mu g? Right, I don't know that right off. Right? What do I need to figure out mu g? I need to know the frictional force, Fsg, which I know, but I also need to know what is the normal force, Fng. So in order to find this, I need to figure out what is this normal force. Let's see, can I figure it out from here? Can I figure out Fng from here? Well, let's see, do I know Fsg? I do, right? So this actually works out fairly simply, that I can, let's see, what am I doing? I'm right here. I can solve this for Fng, and I say Fng equals Fw minus Fsw. Uh, wait, no, I'm sorry. Do I know Fsw? No, I don't know it. I'm sorry. You can't do that. Let me erase this. All right, so now I'm going to write another equation. I'm going to write the equation for the sum of the torques with the axis at the top. Because I've sort of run out of options here with these equations to solve. Is that true? Oh yeah, of course. It's because I need to know FSW, right? Do I know FNW? Okay, yeah, I'm sorry. I had another equation there. So um, I know what FSW is. FSW is, I'm looking for FSW, and that's equal to mu W times FNW, which is zero point 0.5 times 18, which is 9 newtons. All right, so that's our FSW. Now we're still looking for mu G. Well, I still have to find mu FNG. And so now I know that since I know the sum of the forces in the y is this, I can say 9 plus FNG minus the weight, which is 100. That's equal to 0. So FNG is equal to 93 newtons. Okay? And now we can find our mu G, which is what the problem is asking for. Mu G is FSG divided by FNG, which is 18 over 93. And I get about zero point 0.2 newtons. Oh, I'm sorry, this should be 91 here. 91 here because 100 minus 9 is 91, not 93. Okay? This is why it's a take home, because solving these equations it gets a little tricky sometimes, and you have to sort of lay out your equations and think about what your unknowns are. But as you begin to do that, you'll see little pieces fall into place. You'll figure out one piece of the puzzle, and then you have to go out and figure out another piece and another piece, and then before you know it, as those things sort of fall into place, it becomes easier. All right, guys, so again, the process is still the same. You label all your forces. You do the sum of the forces in the x, the sum of the forces in the y. You figure out what is most advantageous for you to do your sum of torques, usually the place where there are the most unknowns. In this case, we chose the sum of the torques at the bottom because it got rid of a couple of unknowns that we didn't know. And then you solve that system of three equations. Let's look at one other one. It's going to be similar to your take-home. This one right here shows a 10-kilogram plank, and I want to know what is this force F if you know that you have this 10-kilogram plank with a 5-kilogram mass there, and it balances on a pivot that's 2 meters from the left end, and it's a total of 6 meters long. What is the force F that's required to hold this into place? All right, so the first step is that you just draw all the forces. Now be careful here because we have a force here as well where the pivot is acting. So go ahead and think about where the forces are. As y'all are doing that, I'm going to hand out a few of these lab quizzes. So go ahead and draw the forces. Think about what are all the forces that are acting on this bar. We have a couple of weights. We have somebody else from my lab that came in. Who else is in my lab? Is that everybody? Oh yeah. This is just for since you have your final next week. Page. Bless you. All right, so what are some of the forces that I have acting here? What do I have? Okay, I have the weight of the plank. So I have a weight that's acting. It acts directly towards the center of the Earth. So this angle is going to be theta. What else? else do I have? The force what? The other weight as well. This is a 5 kilogram mass. I'm going to call this FB, and I'll call this FW, just so we can keep them separate. This also is going to have an angle that's equal to theta. I have this force, which is labeled already, F. That's the force that we want to know. And then what's the other force that I have? Right, the normal force. We'll call it a normal force. It's the force that this thing is pushing up. Now this thing is going to push directly up onto the bar. So it'll be a vertical force like this. So I'll just call this Fn. And this vertical force will be at an angle theta from the moment arm. All right, that angle theta is 70 degrees. I give it to you and I ask, what is the force? Now I want to write the distances. I have this force is 1 meter from the end. Or excuse me, this is 0.3 meters from the end. The weight of the object is going to be 3 meters from the end. I'm told that this is 1 meter, and then also that the pivot is 2 meters from the end, like that. Also recognize that this angle right here is theta. That's my angle theta, 70 degrees. Okay? Now I want to do the sum of the forces in the x, sum of the forces in the y. Which forces are in the x direction? Any forces in the x direction in this case? No, there are no forces here. And then the sum of the forces in the y direction, that's going to be Fn plus F minus Fb minus Fw. All right, now we want to do our torques. Where do you want to do the torques? Where do we want to put our axis of rotation? In other words, what would be the best place to put our axis of rotation? Well, let's write down what our unknowns are. We don't know Fn. We know Fb and we know Fw, but we don't know F. So we could either choose to put our axis of rotation here, or we could put our axis of rotation here. Either one of those would be okay. In fact, any position is okay. But if we put it here or here, that'll make our solution a little bit easier. I chose to do it at F, but it doesn't really matter what you choose. I'm going to put my axis of rotation right there. Now let's do our sum of the torques. I'm going to identify which forces provide torques. It's only Fw, Fn, and Fb. This distance will be 2 meters. The distance from here to here will be 4.7 meters because I have 3 meters. This is another, and then let me check that actually. Yeah, it should be 4.7 because that's 3 meters. This is 1 meter, and then this is zero point 0.7 meters. Or no, this is 1. Yeah, you're right. It is 5.7. Yeah, 5.7. All right. So let's figure out which torques we have. We have this force, and this force. And so we can write those torques. Fw times the distance, which is 3 meters, times the sine of theta, which is 70. Is that going to be a positive or negative torque? Is it going to be clockwise or counterclockwise? Let's see. So it causes, this force right here causes it to move in that direction. So it's going to be clockwise or counterclockwise? Counterclockwise. Yeah, Brennan? Did I get that wrong? It's 3 meters because the board is 6 meters long. You're right. Yeah, so this should be 2 meters. Thank you. And we're actually we're rotating from this point. Thank you. All right, y'all follow what he said? All right. So this should be 2 meters. Thank you. I have to fix my notes. So FW 2 meters times sine of theta, and then the next force we decided is 3 meters, so it's going to be Fn times 3 meters times sine of theta, sine of 70. Is that going to be a positive or negative torque? It's going to cause clockwise motion, so that will be negative, minus Fn, sine of 70. And then the third torque is this Fb, which is going to cause, what's that, counterclockwise torque, I think. So it's plus Fb times 5.7 times sine of 70. And that's all equal to 0. Okay, yeah, that's why I had 4.7 before. Yeah, so this should be drawn from the axis of rotation, which is right here, which is going to be 4.7. All right, you with me on this? On the same page? So I did the sum of the torques. The first FW is it's going to be, I think it was 10 kilograms, so this is 100 newtons times 2 meters times the sine of the angle. That's the distance from here to here, which is 2 meters. This is a counterclockwise torque, so it's positive. This is a clockwise torque, so it's negative. It's Fn 3 sine 70. And then finally we have this third force that causes a torque as well. All right, so if we add all those up, we only have one unknown in this, and that's Fn. So we can solve it for Fn, and Fn works out to be 145 newtons. All right. Now that we know Fn, we can come back up here and solve for F, which is really what we want to know. And F works out to be 15 newtons. So when I put in this 145 for Fn, I know F, I know Fb, and I know, or excuse me, I know Fb and I know Fw, so I can solve for F, which works out to be 15 newtons. Okay? Your problems are going to work out very similar to that. You'll need to draw all your forces, do the sum of the forces in the x, sum of the forces in the y, and then also do the sum of the torques around some axis that gets rid of one or more of your unknowns. How y'all feeling on those? You think you can do those over the weekend maybe, or before the next exam with these examples? Yeah. You can use resources online, though you're not going to find these problems online. You shouldn't. You might find something similar to them, but you can work together, and you can also, of course, use your notes. Alrighty. Um, this other example is a bit more complicated. I'm not going to work through the whole thing, but I'll just sort of outline what you do in this one. You have a number of forces that are acting on it. I'm just going to outline the forces, and then I'll sort of tell you in short how you approach it. Your problems on the take-home are sort of similar to this, but they're a little bit less complicated than this problem. But I just wanted to throw it in here to give you an idea of what some of these static problems can look like. So I have a bunch of forces acting. I have the hinge the hinges is acting on this. This is a sandwich board, like one of those signs that you see with the little chain that holds it together. You have the hinge that exerts a force in both directions, in this case. And then you also have a tension that acts in both directions. They're equal and opposite. The tension, likewise, the hinge is equal and opposite. You have the weight that acts in both cases, Fw here and here. And then you also have the normal force, Fn and Fn. All right? First of all, you'd consider the forces in the y direction, and you would find that the normal force is equal to the weight. You would say the sum of the forces is equal in the y direction is equal to 0, and then from that you would say, well, Fn equals to the weight, because I would have this 2Fn minus 2Fw equals 0, so Fn is equal to the weight. And then the next step that you would take is you would just consider one side of this. Because it's symmetrical, I can just think about one side. So then it would work out very similarly to the ladder problem that we had before. Because it's symmetrical, I can just forget the whole half side and imagine that I have like a wall right here separating those two. And then I can take this just as the ladder problem, and it works out exactly the same as the ladder problem, where I find the tension, I can find the force of the hinge, I can find the normal force, and I know the weight. All right, so I'm not going to work through that part of the problem because it works out very similarly to to the ladder problem. Is that okay? To not work it through? I know it's kind of dry to sort of watch these problems, but it's important for you to be able to do your take home, and these are good examples to help you with your take home. All right. Um, let's just a couple more things, and we'll wrap it up. Just want to be able to know how to derive or how to define these types of equilibrium. I don't know if this will be on your exam 4. I'll let you know as we get closer to it, whether you need to know this for the exam. But even if not, I just wanted to present it. Those of you that going on into engineering, you'll see this in your other classes. So just to present it to you so you'll see it. You have three types of equilibrium: stable, unstable, and neutral. Stable, when you're displaced from equilibrium, that's equilibrium, it experiences a torque or force that opposes the direction of displacement. A good example of this is a pendulum. A pendulum is a stable configuration where its equilibrium position is like this. If I pull the pendulum out to the side, it has a force, the force weight of the pendulum, that moves it back into its equilibrium position. Right, so that would be a stable configuration where the force causes the object to move back into its equilibrium position. You can also have an unstable. Um, when displaced, the force or torque is in the same direction as the displacement. So let's say, for example, you have a pencil that is balanced on the end. You have a pencil that's balanced on the end, and if you displace this pencil, then the force due to weight will continue to cause it to move in that direction. So you can think about these in another way as first stable. The stable would look like a bead in a bowl. A bead in a bowl, if I move it off to either side, it's going to still move back to its equilibrium position. The unstable would be like a bead on top of a bowl. If it moves in either direction, it'll continue moving in that direction, so that's an unstable configuration. And then the third is neutral. In a neutral configuration, the equilibrium is independent of the displacement. Uh, a neutral a neutral equilibrium would be just like something sitting on the ground. That there are no restoring forces to take it either out of equilibrium or into equilibrium. And so it would just be something that that's just sitting on the surface. So this would be the neutral. All right. So in a stable, the restoring force moves it back to its equilibrium position. In an unstable, the restoring force moves it out of the equilibrium position, so it's like the opposite of a restoring force. And then in a neutral, there is no restoring force. The object just sits there. Right? The forces are independent of the equilibrium position. All right? And you can have both of these, like you can have some systems that have both stable and unstable configurations. Can exist in the same system. A good example, I can't draw this, but a good example is a saddle. Because you know a saddle, you have this type of shape in one axis, and then you have this type of shape in one axis, in the other axis. So it's stable in one direction, but unstable in another direction. Alrighty, I think that's it for Chapter 9. There's no homework really for Chapter 9. Really, your homework are those take-home questions. So I think we'll stop there unless we have any questions, and we'll just let y'all go with that. If you get a chance, work on it over the break. If not, that's fine. You'll have a week and a day to work on it when we come back. All right. You have a great day. I'll see you next week. Have a good Thanksgiving.